Our project is High Dynamic Range RF ADCs for Resilient SDR on the Adversarial Spectral skies, done for the fulfillment of the final year project at the Department of Electronic and Telecommunication Engineering, University of Morocco. Our group members are Charik Bandara, Sinal Dampo, Puneet Pereman, Mr. Vijaychandra. Our supervisors are Dr. Chamira Surya from the Department of Electronic and Telecommunication Engineering, University of Morocco, and Professor Arjuna Madanayaka, Dr. Nilanu Deanga, Dr. Igunet Aryaratnan from Deep Silicon Systems Private Limited. Moving on to the problem statement of our project. In the prevailing RF frontends, high-powered local removal is done by introducing local removal filters into the receiver signal path. This approach adds up the limitations such as losing information along with the local removal, lacking the knowledge about the nature of the local removal signal, which if was there might aid military applications. As a solution, we propose an architecture which could incorporate lower precision ADCs and DACs to generate an ADC architecture having a higher dynamic range, which could then be deployed on prevailing RF SoCs along with a plugin for additional electronics. Now, let us go through our architecture step by step. As we know, our main goal is to have a higher dynamic range RF ADC. We propose this architecture which is capable of capturing the quantization noise generated by low precision ADCs and adding them back to have improved precision. In this architecture, ADC1, DAC1 are the prevailing low precision converters. The samples generated by ADC1 are converted back to an analog signal by DAC1 and then subtracted with the delayed version of the input signal to create a residue signal which mimics the ideal residue at the sampling instant. To further fine-tune this, we added a digital fractional delay filter to perfectly match the two paths. Next, this residue signal is filtered to remove unwanted spectral components. Meanwhile, this signal is amplified to make sure that the quantization component from ADC1 is captured by as many levels as possible of ADC2. Finally, the samples from ADC2 are sent through a reconstruction filter to reconstruct the exact quantization noise which was generated by ADC1. This result will be added to the buffered initial samples from ADC1 to end up with our final output. Now, let us move on to the practical implementation of this architecture in the PCB level and its demonstration.
First of all, we are using the function generator to give an input signal. Then we have the power splitter which divides the input signal into two equal parts. Those two signals are passed into our main PCB where we have implemented the proposed architecture. Then we sample the input signal using the ADC1 and send those samples into the FPGA. Then we send those samples back into our PCB and pass them through the DAC. Here we have our analog delay line where we have used a coaxial cable for that. Then we subtract those two signals and amplify it using the residue amplifier. After that, we sample the residue signal using the ADC2 and send those samples into the FPGA. Finally, we take those ADC1 and ADC2 samples into the computer for further processing.
As we are using 8-bit ADCs, we were able to achieve an SNR of 49.09 decibels in the first stage output and improved it up to 73.85 decibels with a 4-bit improvement according to the non-ideal simulation results. According to the actual results, we were able to achieve an SNR of 44.05 decibels from the first ADC output and able to get a 1-bit improvement with an SNR of 50.27 decibels.